Hello and welcome to lecture 4. So if you remember where we are in this course, we have so far in the first few lectures motivated the course. We have talked about the combinational logic in Chisel. So at this point, you can basically do anything you can do in structural Verilog. Today, we're going to talk about how to do sequential circuits, that is circuits with state, things like registers. And then since this is, 1.5 lectures today in person, in the other half lecture following this, we're going to be talking about how to actually start going from what you can do in Verilog to what you can't do in Verilog. So we're moving higher level and really taking advantage of the projections. So what are we going to do for circuits? Number one, talk about registers. How do we do them in Chisel? Show some example ways of building a components with them. Build some state machines. And then in a very timely response, basically in the chatter on Slack about the lab, how can we see what's going on in simulation? We'll talk about both printing and waveforms. Cool. So let's go fire up a notebook, load in the headers. We're set. Okay. So registers, right? These are the way in hardware we, of course, we store data. There's also memories as well. We'll come to those later on. Registers are, the more handy things. So as we're familiar, right, we have a value going into register. If it's a normal positive edge trigger flip-flop, that means whenever this clock goes from low to high, a rising clock edge, we take the value on the input, and that becomes the value of the register. And then from then onwards, the register emits that output value, right? I can change this input at other times the input, and it won't change the output. It only changes when lower values here about the clock signal goes from low to high. The rest of this circuitry here is something I've drawn to kind of give you an idea of conceptually what's going on. This is not necessarily the way it's actually built in hardware. But when we talk about registers, we talk about not just the register holding state, but some other, bells and whistles, right? For example, what do we do on reset? Do we have a reset value? Or what do we do if we want to have a write enable? So you can kind of remind everyone what those things are, right? For example, no register input comes in here. But using these muxes, we can, select what the input's going to be. So let's say, for example, we want to register to only changes when we want it to change, i.e. when it's enable, en is 1. How do we do to set it up? Well, if en is 0, this mux is going to select this, which is going to repeat the old value. So then kind of keep the old value in register until I set the write enable to 1. Okay, then great. Then we'll pull in that next value, and it's being passed on. And is that all? Well, that we could have wired it directly to the register, but instead we have this additional portion in between. We have the possibility of a reset. So if reset is true, instead of taking whatever value we want to put in register from the next signal or even the prior signal, it doesn't matter. This initial value is put in there, right? No matter what, that's the reset. So this is, just a reminder of, in the register, we have this notion of a write enable, which controls whether or not we change values, and this reset, which controls, the ability to kind of set to a known value no matter what. And so not every register has all these pieces always, but I'm just kind of reminding you what they are. And so we talked about before in this class, right, that really, as a designers in Chisel, we kind of just see the value register, both its input and its output. Things like reset and clock are hidden from us, right? They exist. We see them in the Verilog, but they're implicit, meaning they're kind of automatically instantiated, automatically connected, automatically passed through our design. And that's done because it's a common case. The common case is all blocks you have in your module are all on the same clock and all using the same reset. Now, of course, there are times when you may want to have multiple clocks or multiple reset signals. And there's ways in Chisel, and I've linked to it here in the documentation, to do multiple clocks or a different kind of reset called an asynchronous reset. But for this course, you don't need either of these. I'm just putting it out there for those who are veterans who want to see us as possible. Cool. Questions so far? Great. Let's see how lecture looks. Yes, go ahead. That's a great question. The question is, how do I choose which of these bells and whistles and how do I instantiate that? That should be the next slide. So here we go. So when you want to declare a register in Chisel, you have multiple ways of declaring it. And at the end of the day, they all produce a register, which is how much of these bells and whistles are there. And if you want to use the most verbose, most bells and whistle laden register all the time, you can. But a lot of times, not only is it just saving hardware, it's also actually just that, code complexity. You actually don't need those other features. And so how does it work? Well, in Chisel instantiated register, you just say register, right? Like I said before, when it boils down to Chisel, you are instantiating components and you are connecting components. That's kind of the entire ball game. Everything else is Scala code to kind of get between those statements. But at the end of the day, Chisel is instantiating components and connecting them up. So we instantiate this register called R, and then we connect its input and its output, right? So in this case, remember when it's connect operator, this colon equals, it takes the output of the right and connects it to the input of the left. This is not a bidirectional connection. So okay, yeah, so this output goes into this input. Okay, in other words, the input to this module goes into the register, and then of course, same thing here, right? Output register is now connected to the input for this IO.out, which is the output for this module. So great, how does this look in Verilog? Comes out the other end. Here we go. So um, this is Verilog for a positive edge trigger flip-flop, right? There is the register. Here's this always at block. And here is the assignment. So if you're not familiar with Verilog, do not fret. Since this course is not in Verilog, we use Verilog to kind of remind ourselves what's happening here. But we can kind of talk about what's going here. First of all, if you're learning Verilog, you may be surprised to learn that reg does not mean register. You can use reg for things that are combinational or registers. And registers happens in Verilog when you use a reg in a very particular way with an always block in the CAD tools infer to register, right? The synthesis. And I mentioned the reason why this happens that way is because Verilog predates synthesis for hardware generation, right? So it originally made a simulation language, and then when people already been using it, people later learn on how to kind of backwards, figure out how to infer what there should be. And so if you're taught Verilog, you're taught these kind of very idiomatic ways to write registers, in particular, reg_r, always at, and then using the right type of assignment inside here. Alternatively, we've seen the chisel approach. We just instantiate reg. Here's the hardware. We wire it up. None of this weird inference stuff. It is true that in some Verilog design environments, you can also choose directly instantiated register. So here at UC Santa Cruz in our logic design course, CSC 100, we have students directly instantiate the flip-flop register rather than using this always at block. You don't see the always at block until CSC 125, but idea is still there. Cool. We have a register. We're off and running. What if we want to kind of spiff it up, right? Well, we talked about this. Well, if I want a reset value, in that case, I can, instead of using reg, I can use reg init. And of course, the thing here is the reset value. So see the Verilog, and then we do a little tweak, and now all of a sudden, reset has a consequence. Okay, if it's reset, we set it to 0. Otherwise, whatever input is, we can easily change whatever value this is, right? Make it reset to 1. Now, in this case, the chisel compiler is extremely clever and knows that, oh, wait a second. If on reset, it's going to be 1, I can now OR it in there. So remove the if statement there. So as you can see, there actually is some cleverness in the chisel compiler. I'll undo that for a second so you kind of can appreciate that. But it's still all legitimate Verilog. Okay, well, what about these other options, right? Well, what if I instead wanted to use reg next? So notice how reg next not only gives us the reset behavior, it also has, the sorry, reg next. I'm sorry, take it all back. Reg next gives you the reset behavior, right? So you have the reset behavior. It's there. It's also kind of handy because guess what? Instead of declaring input output, the input goes in here, the output goes here. So instead of having 3 lines, it's 1 line, right? So that's small little way to make it a little tidier. And then finally, of course, with reg enable, where we actually have the enable signal. Now we're using the IO enable, and we see that kind of creeps in down here. Throughout these slides, I've linked documentation, so you can go ahead, for example, and say, hey, what is this particular flavor of reg in it? Oops, these are still from the prior slide, but there we go. Here we are, reg in it. It's the documentation created by ScalaDoc, of course, very similar to JavaDoc. And yeah, you can see some information about it, some help as well. Cool. Yes, question. The question is, if I create a register in Chisel and then I care about the Verilog output, will it always produce an always block? Is that the question? Yeah. Yes, that is the way in idiomatic Verilog to create a register is you have these always blocks and you have the Verilog tool infer via synthesis that there are registers there. Now, perhaps you're in a company that doesn't want to do registers that way. Perhaps your company has their own special optimized, awesome registers you want them to use. That would be a great time to use a black box. So you basically make this chisel black box where basically you can have Verilog inside there. Inside that Verilog black box, you can put whatever code you use in Verilog to instantiate your magic registers, probably going to some library and instantiating it directly with structural Verilog. And then the chisel level, you can then just, use that chisel module. But like I said, when it came to this being used in practice in industry, a lot of times um, synchronous registers work for the vast majority of cases. In the times where they weren't the right choice was when you wanted asynchronous reset. And like I said, I'm going to all the details. But asynchronous reset means the reset takes precedence independent of the clock signal. And the reason why you want that is returning your chip on, the clock may not be ready yet. So you have that ability to do that. So it's a very niche real world constraint, not required for this course. But it turns out between synchronous registers on positive clock edge plus the ability to do asynchronous reset, which we've been linked to documentation, that covers like 99.999% of registers in industrial practice. But yes, in certain cases, people have that really fast flop they need, and in that case, they can use a black box. Cool, great questions. Okay, let's keep going. So what might be an easy way to use a register? Well, what if we want to build a counter, right? Counter is something, we holds a value and it increments its way up. And okay, so how does this look? Well, there's some, count value, some number, and then with enable signal, which when it's true, we add one each cycle it's true. So how might we go about doing that? Well, what we just taught you. Well, we have a register, count. Now, all of this complexity is me trying to be clever about sizing this correctly based on the maximum value. So already this is our, V0 design for a counter. From the beginning, we actually are setting a maximum value. And the reason why is when we reach that maximum value, we want our counter to wrap around. So that maximum value may not necessarily be a power of two. It could be, 4 or something, or it could be 5 or something, right? It could be something totally arbitrary. And so we're figuring how many bits we need to hold that value. So it's, the log 2, whatever that number is, stealing to round up in case, it's a not a power of 2. And great, so we'll have that ability to hold that. The plus one's interesting. So if I have enough bits to hold 7, really, if the maximum value is 7, that actually means I can count 8 things. This is 0 through 7. So you have to add 1 to there. So this is a little wrinkle. But okay, there's some logic here to calculate the width. We did it manually. What other logic do we have here? Well, like we talked about a couple slides ago, to do all these various bells and whistles for our register, we have these various muxes, right? So next value, well, if we're below the maximum value, we can add 1. These mux is the first true case of the first one. If count is, greater than or more likely equal to max val, then of course we reset to 0, wrap around. If someone applies the enable signal, great. Then when IO enable is true, we increment the count or wrap around as needed. That's the next val. If the enable signal is false, then we just kind of keep the current value. We don't change count. And then what about the input to this register as itself? Well, we add in one more mux handle reset to set to 0 on reset. And so this is going to be a functional counter. You can see that the chisel compiler successfully, took all these mux logics, and rather than leaving these as muxes on the outside, pulled them into the always combinational block in the Verilog. But for now, you take my word that this, Verilog is correct and it works. Cool. So I'm going to show you in the coming slides ways to use more of these chisel and Scala constructs to kind of clean up this counter implementation. But any questions before I do that? Okay, let's see what we can do in terms of cleaning up that counter. This is functional, this works, but it's kind of a pain to keep doing mux, 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 and handling all these different cases, right? So, but what if we took care of that reset issue with reg init, right? So in this first design, we have 3 muxes, right? We have 1 mux to handle reset, 1 mux to handle the count enable, another mux to handle wraparound. In the next slide, we're going to handle reset with reg init, so we're going to get rid of this mux. Okay, let's go ahead and do that. So we did that. Now we have reg init. It does the right thing. It all kind of comes together there. Cool. One person may ask, but in this case, we have one less mux, so it handles the reset for us. So this Verilog is basically the same. Now, one person may ask, well, gee, what happens if I don't specify the width here, right? Say the default value is 0, which is a reasonable thing to say. It's going to kind of work, and where it breaks is that this tool is under-constrained for that counter, right? It doesn't know how big it is because it doesn't see the maximum value, right? It sees the other portions, right? And so we need this width in order to have it actually handle how big it is, because otherwise, without the annotation, it does not know how big to make that counter. Now, in a larger design, you may have other things in surrounding context to give the inference tool for with inference information to figure out that with correctly. But this counter in isolation, the tool does not know. So it can kind of default to too small, and that's a problem. Cool. Questions? Okay, so now we're down to two muxes. What else can we do? And remember, there's a third mux kind of lurking inside here. It's just we didn't declare it explicitly. Um, what if we did a completely different approach and use when? This is a much more kind of programmer-friendly way to write it, right? We can say, okay, we have a count, still using reg init for the reset value, sure. Then for a write enable, it's a when, right? And so what's nice about this, notice how uh, when this case is not true, there's no otherwise case. That's the whole point, right? We're only changing values when io.n enable is true. And then, yeah, guess what? If we're below the maximum value, we just add one. If we reach the maximum value, the otherwise, then we just wrap around to zero. And we can attach the output to this count. So this is quite civilized, right? This is quite nice. Um, and I'll point out for those of you, you know, keeping track of Chisel components versus Scala references, you may notice here that count is a Scala reference, right? It's a val. It's on the left side. It's a Scala reference. So it points to this register. So, if you imagine a diagram like I drew before, you have, count pointing to a register in Chisel. And then, these other statements here, for example, by putting count on the left and right, it's using that reference. But these connection operations are adding, more connections between these Chisel objects, right? But this one, for example, is, taking a Chisel object for literal one, another Chisel object for an adder, and then adding the one to the current value account using the reference. And then the output of that is being attached to the input of what count points to, which happens to be register, right? Now, it doesn't attach it directly there because it is nested when, statistical compiler is going to figure out the right combination of muxes. We can see with the if nesting down here. But if you compare this slide to the slide 2 slides ago, I would argue as a human programmer, this is far easier to write and to read than the muxes we had 2 slides ago, right? If we go back to these muxes, this is functional, this works, but you kind of trace through it yourself. You kind of think, okay, wait, the output of this mux is passed into this mux. The output, of this mux is passed in here, and you're kind of tracing through it. It's a lot of work. With the whens, you have some nice structure. It's easier to read, easier to write, and we're getting basically the same hard at the other end. And instead, this is a fully parameterized counter. I can change, this counter value, no problem. Still works. It changes the wraparound right here. Cool. Question, yes. That is Chisel. Great question. So log2seal is a helper function that comes as part of your inputs with Chisel. So you may remember, I gloss over it in the labs and the lectures, but we have this kind of this boilerplate we do. And so yeah, this is pulling in a lot of stuff for Chisel. This stuff is setting up Scala inside of Jupyter, which is not normal. That's that portion. Scala inside Jupyter. This portion you'll see in a lot of Chisel designs. Depending on Chisel design, you may not need to have every one of these imports. I kind of include all of them out of safety. This one you definitely need to have. I think log to seal is probably inside .util. That's probably why that one's there. Chisel test, as you've seen, we use testers. You can write Chisel without testers. One particular test we like to use is the raw tester. And rather than writing, chisel test.rawTester.test, you may have seen in some of the slides, I just write test because I imported it directly. Treadle also do simulation. You'll see that later today. But yeah, the peak poke. Yeah, exactly. Chisel test is the peak poke stuff. So I think maybe in about a slide, if not 2 slides, you're going to see me use a test. And that test block, even though it just says the word test, it's actually from chisel test. And that's what that long import is kind of pulling in for us. Great questions. Okay, so here's the when. I think this is a nice way to write the counter. How else could you do it? Well, I told you about this reg enable, and guess what? It can kind of be like two muxes in one, like I showed you, right? It can handle both the reset and the write enable. So of the three muxes we had originally, that handles two of them. The third mux, of course, is the wraparound mux. I put it all in one line. I'm showing you, yes, you can write this all in one line. It's a pretty dense line. I'm not endorsing this, right? I'm just showing you it's possible. And yeah, you can see it all kind of comes together. In this case, we pulled the width inference into the output port, and even though the register itself didn't specify that, Chisel on its own kind of figured it out. You know what? This register is attached to something this set width. I'll make the register match. So that's why that works out. Um, but yeah, I would argue this is not as ideal. I prefer the whens. Part of this course is kind of looking at what it is code choices. These are both functional correct code. Which one's better? And I think this one kind of makes the intent more apparent. This one, yeah, technically it's fewer lines, but I don't think that's easy to understand though. Cool. Yes. Well, so reg enable, despite the name, is both an enable signal and a reset value. So it's those two things. That's why if you go back a few slides, I kind of showed you this mental model register. This isn't quite necessarily the way it is in hardware, but conceptually this is very accurate. You can kind of think of the write enable and the reset as kind of two muxes in sequence before you get into the register. But in the actual hardware, the synthesis tools and hardware tools may choose to do it differently. Some hardware families have different registers instantiated depending on how you're using it. Other ones don't. That's kind of, the low level deal for this course. But yes, that's all possible. Cool. So here's that test we're talking about. So yes, this test has this nice concise name because I have that imported earlier. So this is a test of the counter. And this is an exhaustive test, but what do we do? Well, we say I want a counter with maximum value 3, turn on the enable, and say initially coming out of reset, yeah, it better be 0. Now, one thing you've not seen yet is this next thing, where we advance the simulation by one cycle. Before we had all these test cases that were purely combinational, we changed the values and then we checked the values right away. And unbeknownst to us, the simulation environment is actually executing that. So it makes combinational signals appear to take 0 time, right? They have their input immediately changes the output combinationally. There's no delay there. However, clocks, that is something intentional, right? Register only changes its value in a clock cycle. And so as a result, you know, in order to actually change it, see the next cycle, we need to actually have a clock cycle pass. Okay, so one cycle goes by, we enable on, now we're 1, now we're 2, then we reach a 3, the maximum value we said we should. And then we turn off the enable, so it stays at 3. Then we turn it back on, and we see it wrap around. Cool. And as I said before, with these test cases, right, when it executes normally and there's no issues, it's silent, right? And the reason why is you're supposed to have many, unit tests. They all run. Hopefully, they're all green. Anything goes through, and then if one of them fails, then we want to know. Let's say, for example, we change our maximum value to 2. Well, then our counter better not reach that value 3, right? That's what we're going to see, right? We're going to see, you know, IO out 0 did not match 3, and that's because when I got to 2, that logic for wrapping around kicked in and wrapped it around back to 0 rather than let it reach 3. Likewise, let's say I changed the maximum value to 4. Now it's a different problem, right? Where we had to wrap around with this test case. However, it's wrapped around too soon, right? And so you may be thinking this test case looks extremely brittle, and that would be a correct assessment. But that is okay for today, right? Is this kind of the course, right? Get something working, move on, and then come back when we need to fix it, right? And then come back when we need to fix it is, yeah, wouldn't it be great if our test case was also parameterized? They could, match whatever, maximum value the counter has. We'll do stuff like that in coming lectures. But for now, you can it's a lot of tedious work, but you can do it. You can write out all the signals you expect for every cycle. And technically, you're not required to write every cycle. I could only include, the pokes when they change, and that should be sufficient. Yeah. So only need to technically change the pokes when they diverge, but you can see with copy paste, it's probably easier to just include them always for verboseness. Cool. Question, yes. Great question. So clock step seems to go by one cycle. Can I do any other units? Uh, yes, those units need to be positive integers of number of cycles. So you can't do half a cycle. The environment we're using the simulation for, there are no semantics for anything of finer granularity in a cycle. Combinational logic is instantaneous. Registers take a cycle. There is no other differentiable unit of time available. Now, if you're writing pure Verilog by yourself, this is exactly the same, right? If you're writing pure combinational Verilog, it is effectively instantaneous. If you are a register, it does take a cycle. Now, where the Verilog starts to kind of show some differences are things like a negative clock edge. Well, these are positive registers, so you're not going to see that. Another place Verilog might show this is what if you have a latch rather than a register? Yes, you can do latches in Verilog. Most design houses are very restrictive on when you can use them. In Chisel, they're not built in. If you want to put them inside of a black box, you can, and then simulation is going to be a little wonky. The third time in Verilog is in Verilog, you can put this, percent specifier, or this pound specifier to have an explicit delay. That's a simulation only construct. That's not a synthesizable construct. That's that delay parameter. It's that delay parameter is because it's not synthesizable, it's not in Chisel. So yeah, so Chisel simulations, everything is going to be uh, integer number of cycles. Now, in this case, let's see if we can't be a little ambitious. And what if we step by a couple cycles, right? So if I step by 2, this should be 2 by then. And the answer is yes, right? Because yeah, if I left it alone, yeah, so whatever number we put in here is number of cycles. I can do 0, I guess, and say it shouldn't change. But by default, it's 1. We don't even need to write it. Great question. I can, unbreak my test case. There we go. Cool. Other questions? Great. Working again. Cool. Okay, so we've built a counter. Kind of recap where we are. We've built a counter 2 different ways. We've seen this kind of register construct in practice. In the day, we say we want to register, we declare it, we wire it up, and these different nuances of reg init, reg next, reg enable, those are just ways to kind of get some of that stuff in terms of reset, write enables included for free, but aren't strictly necessary, just a way to make the code a little bit more concise. What else can we do? Well, working our way towards a state machine. So for a state machine, in addition to having registers, to make our code well structured, we're also going to want to have enums, or in other words, enumerations. It's a way for us to assign human chosen names to numbers. So that way in the code, rather than saying, this register is value 2 versus value 3, I can say this register has value whatever state I care about versus state A versus state B, right? And so in Chisel, the way to do this is something called a Chisel enum. And if you're looking around documentation, some of these names are all very similar. So I try my best on the slide to differentiate them. So Chisel enum is the construct to use. If you see very old Chisel code, you may see enum. That's the prior way in Chisel to do enumerations. And so this language is constantly evolving. Likewise, in Scala itself, not in Chisel, something called enumeration. So Chisel enum is the magic one. If you forget, you can use this link here and go read documentation. Here we go. And so what do we get? Well, it's a little bit of boilerplate code here, where yes, instead of class, it's object and it extends. Technically, this is using object-oriented inheritance. We haven't covered inheritance yet, so for now, you can think of this as kind of some boilerplate code, but basically what do? For all the enumeration values you want, you put them on the left-hand side of an equal sign with commas separating them, and say value. What is this value? This value comes from Chisel enum. If you want to set the value to a particular number, you can. You can assign it. You can have multiple ones per line. That's all possible. And so what do these turn into? Well, these enumeration values turn into uints of the right size to kind of hold the maximum value of that enum. So to kind of see how this plays out, here we made a demo enum with name A, name B, name C, and name D, right? And name D we're setting to 5, and we can see thanks to 2 string methods, we can see how this plays out. Okay, so name A is 0, name B is 1, name C is 2, and because I told it to, name D is 5, right? And so yeah, this is kind of an enum. So we'll see this in just a second, but for now, you should use this boilerplate. Like I said, maybe you prefer to write this. Oops, let me write it out. And then val name B. This should also work. Yeah, no problem, right? And that's one of the things, whenever you have enums, right, as a hardware designer, a lot of times you don't care what the number value is. And the reason why I use an enum is rather having this risk of your code of, having this magic number floating around your code. Okay, you have some comparison against 2, comparison against 3, and you change in all places. enum, right? Single source of truth. You define enum in one place. Everyone who uses that enum can then be in sync, and that way when you change enum, all the users will change at the same time, right? And so a lot of times you really don't care what the value is, and you can just let it use value. Sometimes you have a certain number you want. So sometimes you may use an enum, for example, to parse something that's already known. That's a helpful thing to do. Cool. Okay. So let's now build a state machine, right? We have registers, we have enums that label our states. Let's build a finite state machine. So here at Santa Cruz, of course, our unofficial mascot is the raccoon. At least that's my opinion. Official mascot, of course, being the slug. Um, and so what do we have with the raccoon? Well, this is the behavior I made up for a state machine. So by default, in the finite state machine, we have this notion of states, right? So four possible states, and these states are also kind of outputs in a way. So, what is the action the raccoon is doing? Is either hiding, wandering, rummaging, or actually eating food. In this finite state machine, when you see a blank arrow in just one of them, that means that's the default initial state, right? So it tells us, okay, when the state machine starts, we're going to start in the hiding state. If raccoon hears no noise, so not noise, it's going to sneak out and start wandering around. If it manages to find trash, that's what these arcs from our state machines are. If that condition is true, you change states. We're going to go rummage through the trash. If we find food, great, we can eat that food. If I don't find food, shucks, gotta go back to wandering again. If at any point we hear noise, we're gonna go back to hiding, right? We're gonna go hide away. So this is, a four state machine for a raccoon. I think it's really helpful to kind of draw these out by hand first before we go ahead and code it up. Okay, so let's code it up. Well, we can do that. So we have our enum. So we can now assign names to these chisel states, these raccoon states, right? So our rack action, what's it doing? Well, chisel enum, so it's either hiding, wandering, rummaging, or eating. The actual state machine itself, we have the inputs for, noise, trash, and food, and then the output is whatever action we're doing, right? Which is one of these, from enum. Now our state is a register, right? So we're kind of keeping persistent over side time. And we use the init field, right, to kind of that default coming out of reset to be the hiding with state. Okay, so we're in the hide state. So you can see we can refer to these enums with, the object name and then dot hide. There is a way to include the internals to remove this prefix, but I think it's more clear to kind of have that more verbose name. Okay, what do we have? We have a when. Okay, if the state is hiding, what do we do? Well, as we go back to a slide, remind ourselves, okay, in hiding, we're worried about the transition to cause to leave this state. Well, if there's no noise, I go to state wander. So yeah, hey, if I'm in state hide, when no noise, state changes to wander. So notice how inside this case here, there's no otherwise, right? So the otherwise is implicit in the sense that if I don't change my state, the state stays the same, right? That's what the when does for us. So I don't have to bother saying, current next equals old state. Default, no, it's already handled, right? If I didn't change state, state maintains its prior connection. That's one nice thing about registers. Yes. Uh, Great question. We're going to try it out because I don't know the exact thing that's going to happen. We know it's not good. So the question is, if I didn't use reg init, how does this break? Let's find out. Um, so first, it needs a type, right? Okay, so type should be rack action. It's spooked about the types. So what if I know that rack action should be a uint and see if I can trick it? It is too smart. So you can see what the compiler is telling me is, hey, 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 you have a uint and you're trying to assign that to a rack action. That is not a rack action. How dare you? So now I'm gonna try and use the rack action.type and see if that'll work. There is a way to do this, but I'm actually not sure, so I'm kind of having fun with this. We're gonna try get class. It's probably also gonna break, but yeah, okay, I have homework. I will post this on Slack. what the answer to this question is. So what could happen? Oh, we even wrote a notebook. We're all at it. Okay, so notebook itself broke, but in addition to that, um, what should happen? Well, independent of chisel versus Verilog, if you don't set the value register, its value is unknown, right? That's always kind of the case, right? The value it has could be totally arbitrary. So if we don't know its initial value, which of these clauses applies to it is a little bit dicey because there's no initial value, right? You can imagine with some really clever theory, maybe you have some sort of very complicated set of logic such that even if the initial value is unknown, somehow the conversion is some known state. That could happen. But in general, it's good practice to have registers get into known states. Most of the time, it's accomplished by a reset signal and a reset value. Sometimes it's just because the register has an input, the input has a known value. If the input has a known value, then that gets the register into a known state. Yeah, so how to figure out how to declare the reg by itself without using an instance of the dot hide. I'll post that on the Slack. Good question. Other questions? I can keep talking about the rest of this schematic here quickly, right? So we kind of see, okay, state is hide. I do that. If the state is wander, going back a slide, right? We had two exit arrows, one for noise, one for food. So notice how I say when noise, yeah, we change to hide. Else when, if there's trash, we go to rummage. And so the way this logic is written, there's actually kind of a precedence here, right? I'm saying noise is a higher precedence than trash. Um, Technically, if you're a purist, going back to the prior slide, the way the state machine is written, it is ambiguous if both food and noise is true, what your next state should be, right? Because they're both valid solutions. You only can be in one state at a time. If both food and noise are true, where should you go? This state machine is underspecified. For today, I'm going to kind of wave some magic hands and say we can assume only one input is true at a time. So either only noise, only food, or only trash, and thus that scenario can't happen. But if you're a purist, yeah, I'll readily admit that that's underspecified. But yeah, so you can kind of see how this fits together, right? When's nested, else when's. This is totally reasonable code. I did a little bit of extra spacing to try and make some things easier to read for the formatting. Of course, the output is about as register. Yes, there's Verilog down here, but you can see it's, a lot. The Verilog is always kind of internal muxes. That's how it kind of gets mapped out. And there's, of course, there's the default settings of the registers, but that's not important. I'd focus on this. Other questions on this state machine implementation? Cool. Okay, so let's see how else we might choose to write this. Um, well, what if we use the switch construct? So switch is a Scala construct that is similar. Sorry, let's take it back. Switch is actually a Chisel construct that is similar to what you may see in other languages. Um, Scala uses match normally. Apologies. So switch actually is from Chisel, not from Scala, but it does what we expect it to, right? I can say switch on the state, and then what is the state currently? If the state is hide, then this block occurs. If the state is wander, then this other block occurs. So yeah, using the switch statement, this is a lot more tidy. You can also notice in general, right, by using this enum, things in general are a lot more tame, right? We have the state names being clear, the next state names being a lot more clear. This is much nicer code than having like raw numbers. Remember, okay, number two is this, number three is that. Use enums, right? Kind of keeps things all tidier. Cool. And yeah, I can print Verilog. The Verilog is going to be not exactly the same because the way Chisel maps things, but performance-wise, indistinguishable. Cool. Other questions? I took the time to handwrite a test case, and so it doesn't quite traverse every arrow, but traverses a lot of them, so we can kind of trace through it. Yeah, hey, so if I originally have noise uh, and I'm in hide, I'm gonna expect a clocked step goes by. It better be hiding, right? The raccoon should be hiding. Okay, then I remove the noise, advance time. Now moves on to wander, right? That's right. Then I, set trash to true. Advance time goes into rummage. Then I, turn trash off, turn food on. Advance time, it goes to eating. I, you know, leave food on, it keeps eating. If you go back to the diagram, you'll notice when you're in the eat state, you basically, there's no food arrow keeping you in here. It's more just you're only going to leave on noise, right? Okay, so only going to leave on noise. Um, and eventually there is noise. Time goes by and we'll go back to hiding. So yeah, this checks out. This is a manual test case. We'll talk about all quarter how to kind of write test cases in a way that's more programmatic and less, manual and less error prone. But it's good to kind of have this, right? Eventually you get to a point where you have a module and a test case and two of them working together. This is kind of the modality we have most of the quarter, right? Where we're going to make hardware generators and then we're going to interact with them in simulation with test cases. Now, of course, in other scenarios, you'd probably make hardware generators and pass it on to a CAD tool to get turned into physical hardware. That's a great thing to do beyond the scope of this course. This course is mostly what's called front end design, writing a generator, testing, making sure it's right, and that kind of stuff. The physical design optimization is obviously extremely important. Couldn't squeeze it into the quarter. Other questions? I should put a asterisk on that. I will talk about chisel considerations for performance as the quarter goes on, but we won't be using ASIC CAD tools. That's a better way to say it. Okay, cool. So we just had, these test cases, and yeah, I mean, ideally your test case passes, so there's nothing to look at. But what if you want to debug it? We had this question on Slack just last night. What else can we do? Well, with Peak Poke Tester, it's not obvious, but believe it or not, under the hood, what's happening is the environment is taking Chisel design, instantiating it in simulation, running your design in simulation, and using whatever stuff inside your chisel test to, prod your design, right? So, when we poke signals, we're setting inputs. When we peak signals, looking at outputs. And of course, expect is how we look at things. There's also the ability to advance time. So how else can we interact with our design? You have two ways of going about kind of seeing more from your design while simulating. One is explicit print statements. A lot of people are, printf debuggers. Uh, that is possible. One thing that's really nice about hardware, I encourage those of you who have more of a software background to try embracing this quarter, is waveforms. So, when you do print statements, you the human is saying, you know what, I want to print this particular value, maybe put constraints on it. I want to print this particular value under these constraints. Put an if statement around it. With a waveform, you get all values for the entire simulation. So what's cool about that, as you're debugging, you run the simulation once, and you can trace your way through the waveform. So you kind of are navigating that waveform. You only need to run simulation once. With printf debugging, typically you put a printf in there, see the value, and like, oh, that's surprising. What about this other value? You need to add another print statement, another simulation run, and you're kind of repeating. So um, waveforms are typically a better practice to use for hardware design, but guess what? There are some times where prints are really handy, so we teach you both. And whether you use print statements, waveforms, or both, remember to use it for debugging. When it comes time to running the test, that test needs to be automated, right? So what do I mean by that? We don't want to have someone who says, okay, yeah, run this thing, and if that print statement on the fourth line says 15, it's correct. Like, you don't want to hear someone say that, right? Because that's maybe okay when you're developing initially and debugging initially, but you want to put that logic of knowing what to check and what the right value is into a test case. A test case is both an input and expected output. And you want to put that intelligence, that insight into a unit test, right? So in this case, a chisel test. And so your chisel test is going to check what's correct, right? So it's going to be, those inputs and then the expected outputs and making sure they match up. The stuff with prints and waveforms, that's only for debugging, right? It's only making sure these kind of check out. So let's kind of see these two things in practice. So for printing, technically you can print in two different times. You can print in Scala while the design is being generated. So it's not in simulation, it's while your hardware generator is running. You may have seen this command already. It's this print line command. So yeah, as you'd expect, takes a string, prints it out to the console. Scala has a little bit of extra flourish. It has string interpolation. So if you've seen these in Python with an F, it's very similar where you have the ability to kind of, mark the string as starting with S. And then inside there with a $sign, you're actually going to include variables. So in this case, for example, I have my val4. And so this string, when it prints out, is actually going to say, what my val is and actually even call a method on my val. Now, if I just omitted that S, the string is now just a raw string. So now I get, the raw contents of the string. But yeah, if you've seen in Python F strings, this is very similar. This was called string interpolation. It's the more broad concept. Cool. Okay. But now how about the printf debugging I was promising a second ago, right? So if you want to print during simulation, you use printf. This is a chisel thing. This is not in Scala. So how does it work? Well, much like the original C printf, there's a format specifier string. And then if you have any, variables you want to substitute in there, you got to use this weird, percent syntax. We've seen this before. In this case, percent %d means print an integer, and then you give it that, argument as a, comma separated list of arguments. This is very much like classic printf. Um, if you know C, this is very familiar. However, you might take a more modern style and once again adopt interpolation. And yeah, we can do that too with chisel. So actually, we can interpolate the value just fine if you use a p. So that was something someone in chisel's side chose, for printf, interpolation string. Yeah, so this is not normal Scala. This is something for chisel. But yeah, if you want to use this printf with the interpolation style, you can, include raw strings as well as a variable to be substituted. And this will be substituted as simulation is running, right? So um, here we have a counter from before, but I wrote it using the when syntax, sure. And I chucked in a couple printf statements in there. So now if we set this up, on the next slide, go ahead and run it, what happens? Okay, well, what do we see? Well, I told it to run for 5 cycles. We talked about this a second ago. Um, and we see, incrementing to 0, incrementing to 1, incrementing to 2, wrapping 0, incrementing to 2, incrementing to 0. Okay, so what do we get? Well, um, that's a fault of my test case. So for those of you who are paying attention, you like said, incrementing to 0 seems like a weird thing, right? If I go back a slide, like, wait a second, it says 0 twice. Why does it say 0 twice? Um, that's actually, I would argue, a confusing use of English here. Incrementing from might be more clear, right? In which case, what do we get? Yeah, incrementing from 0, incrementing from 2, incrementing, etc. And then now my 0 is misformatted. Once again, printf debugging tends to lead to multiple executions, as always. So here I am, constantly running and tweaking my setup. But there we go. Okay, so that's perhaps more clear, incrementing from versus wrapping. But yeah, that worked. We did the printfs. This is kind of the old school style. Maybe the interpolation style is, you know, uh, more friendly. So I got you see me kind of rerunning to reevaluate this model and I change this code, and then rerun the simulation. Cool. Questions? Cool. So that's how to do printf stuff. So then what about waveforms? Let's do a waveform. So we got to do a slight tweak to the arguments to the simulation. And for now, you can treat it as boilerplate, but this is turning on waveforms. So for those unfamiliar with this term VCD, that is short for value change dump. That is the most common format used for waveforms. There are other much better formats, but VCD is kind of this classic canonical one. So we have it a lot of places. So if I run it, looks the same. What happened? Well, deep inside a folder, it has a .vcd file. I've already, in advance of this lecture, on a prior execution, dropped that folder into a waveform viewer. So waveform viewer, of course, you've seen a lot of these. For example, here in courses you use in CSC 100, you've seen the Vivado environment. In CSC 125, people can correct me in the room. I imagine you're using this one, which is Surfer. Yeah, yeah. So Dustin loves Surfer. I recommend Surfer. Surfer is quite new, and it's quite good. So Surfer is a open source viewer. This is actually literally running in a browser window. There's a way to download as a native app. There's a lot of waveform viewers. There's classic ones called GTK Wave. On Mac, there's one that's outdated but still somehow works, even on ARM, called Scansion. There is a few other waveform viewers out there. There are waveform viewers that are built into VS Code. There's even a waveform viewer that can run inside JavaScript, which you used to use inside Jupyter Notebooks. The reason why I'm not running that here in this lecture is because the formatting is kind of whack. It's not quite the right CSS, but otherwise it's fine. There's a lot of choices. Okay, so how to use a waveform viewer. It's already loaded in the file, so I did this correctly. to load the file in. And you see, well, there's nothing here. Well, there's actually this object, and it has these internal fields, right? Something like the clock. Now we can see the clock value varying over time. So interestingly, the waveform viewer has decided to, associate time with this. I mean, yes, desimulation has a clock signal that changes, but the fact it has a certain number of nanoseconds is completely arbitrary, chosen by the simulator because we didn't actually specify time anywhere. Sure, we have a reset. Put that in there. You see that we never in our test bench, if I go back a slide, in no place did I set the reset value. But by default, this test bench will start simulation and reset on and then turn it off after a cycle. And that handles a lot of cases. Sometimes maybe that's not what you want. Sometimes you want to control it manually. You can poke reset, no problem. Um, but yeah, that's what we just did. Cool. So we have our, clock and our reset. What about the count value? There we can see it, right? Initially it's 0. Maybe I should also turn on the enable. Maybe I'll move that up a little bit. Yeah, so you can see, okay, turn the enable on. And guess what? When the next rising edge enables 1, we add 1, right? Next rising edge enables 1, we add 1, we get 2. Next rising edge enables 1, we get 3. And then guess what? The wraparound occurs and that happens. So those are the main values here. Technically, IO out is the same as count, right? We saw that. And I actually don't know what we're going to see in the waveform for these print statements. It might be kind of gross or nothing. So I wouldn't worry about that. Cool. Questions on that? Yes. Good question. I hid that because it's gross, but I should actually show it to you. So teach the controversy. All right. If I go into my terminal where this is running, I am currently in lecture 4. Folks can see inside my terminal of all the things going on in here. And yeah, homework's already posted, by the way, so you don't need to have those tabs there. What do we have? Well, we have the Jupyter notebook for this. When I'm running things like generating Verilog or running other stuff, those Verilog emissions create, these various files. You can delete those. But okay, in test run dir, every simulation I run creates a new directory, which is a little bit, annoying because they're all, numerically tagged. And so it's like, shoot, how to find the right one. Depending on your environment, there's a way to go in and set a flag to have it keep reusing the same test directory. So that way you can always know to find the files. Let's say I didn't set that flag. So how do I know which one to run? Well, I can look at the timestamps and see, yes, this is the one that's the one most recent. So then I'll go to that one. And great, there's the BCD file. Now, how might I get this complicated path into the window we just were looking at? I'm going to sheet for that. I'm going to exit full screen. I'm going to say choose file here. And so yeah, I already had directory previously, but let's say I didn't know that. On Mac, one trick you can do is open up the folder and then just drag it over. So that technically changed which directory I'm in from the one from right now as opposed to last night. Load it in, and yeah, now we're cooking again. We can load in our clock again. Actually, I want to show one other thing that I think is a good thing that was pointed out a second ago. So I was talking earlier about the timing specificity. One nuanced detail. So chisel test in this particular case is not anyhow specified. You can see different things we're manually changing. Things like IO enable is happening on a half cycle phase, right? So that way it makes it more clear for people reading these waveforms that, oh yes, this changed before this clock edge, right? But that's not a strict requirement, just the way I happen to run the simulations at a particular time. Cool. Other questions? I think that's almost it. Yes. So one other thing that comes up a lot when you're trying to write more sophisticated tests is you often want to have bigger and bigger numerical literals. So you've seen already in lectures how we have, .u, .s, .b to cast, uint, sint, and bool. But you also can do things with the spacing as well. So rather than having everything be a decimal, We can use strings and actually have format specifiers. We can have, binary things with B. We can have hex things with H. We can put underscores anywhere we want to separate things out to make it easier to read. And of course, whatever comes out, we can, make it as a uint. We can make it as a uint and set the width. Rather than .u, we can say .as uint. That's the same functionality, it's just more verbose. And yeah, these are all going to be, various uints of various sizes. Cool. Any other questions? Great. Okay, well, that concludes lecture 4. We'll be doing a half lecture in just a minute.